Okay, so just to like talk about computability itself for a minute. So computability, right, as I was just saying, is the from lecture 22 is for a Turing machine at least, which is the only way we have it defined, but you can generalize the concept. Is that your a language is decidable if there is computable if there exists a Turing machine that for any input says yes, this is in the language, or no, this isn't, in some finite number of steps. So it's always going to give you an answer, yes or no. But I want to make sure, like, you guys understand then the difference from some things that are uncomputable, like the halting problem. Are you guys familiar with the halting problem? Has he gone over it? Has he?
Briefly, like all things.
Yeah, I think I thought he put it in there, but I guess I don't think there was any questions on it, and I think there's like footnotes. So the halting problem is you have a machine so a machine that decides the halting problem would need to take its input, the description of another Turing machine, and an input to that Turing machine. And it just rejects if the Turing machine is nonsense or something. Like if the description doesn't make sense or the input doesn't make sense. But let's assume then that it's one of the interesting cases where you've got this input machine and this input to that machine. So your machine wants to decide, does the given input machine, let me put something up to make this easier, because there's two machines going on here, and that makes it a little complicated. So let's say we're trying to get a machine H that decides the halting problem. I should actually, I keep forgetting to check if this is actually a formula on the screen. Yeah, good. But I should probably use black, because I think black shows up better. Actually, that's showing up fine. So our supposed machine wants to take as input we don't care if it accepts or rejects MX. It just does something. The point is we want it to, it's like just, because some things can loop forever, right? Like some machines could just loop. You could have a machine that writes a 1 and then goes to a state where it erases it and writes a 0, and that brings it back to the state where it reads a 0 and makes it a 1. And it's just like, you could just do the same thing. It's not a useful machine, but it is a machine that is a valid description of a Turing machine. So this is not going to be computable. But what if I give you an M and an X in the language?
Wait, can you say again what do you mean? What is the reference to this when you said this is incomputable?
I mean that you can't come up with a machine H that does this. That does this.
Okay.
But there's an interesting property worthy of noting that's relevant to computability, in my opinion, and something you don't necessarily think about when you first think about computability, which is to say that so for the language of H, which is all the language of H is all inputs that are machines and X such that MX halts, right? If I tell you MX is in the language of H, can you build a machine that always halts? That always would the machine halt H? Something's in the language. Yes, weirdly enough.
Are we, because we're taking it as true that it is in the language?
Yes, right. Just as a hypothesis. So actually, you can easily build a machine that always accepts when M and X are in the language. Because all you have to do is you simulate M on X, right? And if it halts, then by definition, it only took some finite number of steps, and then you accept. The point of this problem, we're not going to prove that this is not computable. You can just take my word for it, unless this lecture tells me to do that. I haven't read the full thing. But this is not computable because you can't build a machine H that halts and accepts or rejects on all inputs. But you can definitely build one that recognizes the language, like it always outputs accept when it sees something in the language. It's just that when it gets an input that's not in the language, it might run forever. Because basically this tactic of simulating M on X, if it's not in the language, then it doesn't halt, right? By definition.
So it can tell you yes, not
read
no.
it, or what?
because it's in some loop. So like MX might be a machine that doesn't halt. Here, I'll give an interesting. So like think about, what if I have a machine that, this is my read-write head, okay, and this is my tape. I'm just going to draw it pictorially instead of using the formal definitions because I think it's going to be easier to parse like intuitively, and we're just working in an intuitive level right now. Okay, I'm going to build this machine. So this is a machine M, and I'm going to say that in its first state, let's call it state 0, if it sees a 0, it writes a 1 and then moves to state 1. And let's say, so I mean, there's many ways to define a Turing machine. Let's say the Turing machine doesn't have to move left or right at every step because this just simplifies what I'm doing. And I don't really care what it does on the other inputs because I'm just trying to do a simple example. And then your accept state is here. Let's say it moves like 1, writes 1, and then it's like going to move into this accept state where it loops. So this machine does technically accept on some inputs. But if I give this machine 0 as an input, and that's the only input, what does it do? Writes a 1, then moves here, writes a, like, you can define infinitely many different machines that would just run forever. It's never going to reach this accept state, never has any reason to halt. It just keeps reading and writing the same thing. For determinist, for like finite automata, this never comes up, right? Because you have some finite string that's your input, and you only ever look at each bit once and do what it tells you, and so it stops after that many steps, right?
Wait, so trying to understand conceptually, you can always check that h of mx equals 1, but you would never be able to check that it equals 0 because
Yes.
it would just keep going, not knowing if it's ever going to halt.
Yes. So there's actually a way to formally prove that. Like there's a mathematical proof for that. That you can't come up with a machine that is going to be able to decide this language.
And that's why it's not computable.
And that's why it's not computable.
Okay.
Not because it like never works, but because you can't get it to always accept or reject when given some input. Like the input is in the language or not in the
So it has to
language.
work on all inputs
Yes.
to be computable?
Yes. In some finite number of steps.
Okay.
Because it's not like every input is either in the language or not, right? The machine, like it should accept or reject on each input, but there are some inputs it's not going to be able to halt on.
Mm-hmm.
So that's just an example of it that I think improves maybe intuition.
Oh, in finite steps. That's the key.
It's a finite number. It needs to halt in a finite number of steps. And you can see why this would not work very well in the case where something's not in the language, right? Because the obvious machine to build is one that simulates the steps of M on the input X. But if it doesn't halt, then what it's simulating doesn't ever stop.
Right.
So it doesn't know to stop the simulation. It never knows, like, your machine H is always going to be in this position where it's like, okay, like maybe this doesn't halt, but maybe if I take one more step, it halts.
Mm-hmm.
And then like at every step, it's like wondering, like it doesn't know, it can never know to reject because it might just be a couple more steps.
But all of these are in the language in this case.
I was just using that as an example of, I was just trying to, when I was saying that for all M and X in the language, I was merely trying to point out that if I gave an input that is in the language, it's not hard to build a machine that does what's called recognize the language, which is it always accepts in a finite number of steps if an input is in the language, and we don't care what it does when the input's not in the language. That's different than computable though. So he doesn't actually define computability here. He defines it in lecture 22 with respect to Turing machines. But yeah, okay. So I just wanted to make sure people kind of understood, given that this is computability, basic computability, but he doesn't even define computability here. I just want to like go back a step and like talk a little bit about the intuition for computability. Now let's just make a different video.